Hello, pre-calc honor students. Here are their last section of Chapter 5 on exponential equations and changing bases. I'm actually going to start by talking about the changing base formula here. And if you have log base b of c, it's equal to log base a of c over log base a of b. Which, if you decide on your base a to be base e, it's natural log of c over natural log of b. Or if you decide with base 10 common log, you could say common log of c over common log of b. This is going to help you calculate for any unknown power. Now on the T89, you actually don't have to use the change of base rule. You can use log base c as log, which is, you get that with diamond 7 to get log, c comma b, where the second thing in the argument here is what you're using for the base. And this is the input number, c. If you leave out the b, it just does the common log base 10. Now here's a little proof of this formula. How does this work? We want to prove this part of the formula like this. Well, let's start off by just letting m, any old number, equal log base b of c. Now we can rearrange this with our ideas of logarithms. So that's b to the m equals c. And now let's introduce the new base. Take the log base a of both sides equals log base a of c. Okay, good so far. And then we can use the bump the log rule. M times the log base a of b equals the log base a of c. And so m equals the log base a of c over the log base a of b. But what was m? M was the log base b of c. So the log base b of c equals the log base a of c over the log base a of b. And this kind of makes sense because if you change the base of the log, you're not going to get the same thing. So if I took this out, this wouldn't be necessarily true. Log base b of c doesn't equal log base a of c. So you divide by a correction factor, which is the log base a of the old base. Now let's apply this to the problem. In 1990, there were about 5.4 billion people in the world. If the population has grown at 1.95% per year, estimate the year when the population will be 8 billion people. So we put our 8 billion in for the new population. Our initial population, 5.4 billion. 1 plus the rate, which is 1.95%, which you have to change to a decimal, 0.0195, raised to the t. So we're going to divide both sides by 5.4. And this is 1.0195 raised to the t. And now here's where you have a couple of options. Option 1. That is, just change it to the base you've got here. Change it to a logarithm. T equals the log base 1.0195 of the other side, 8 over 5.4. And we can put this into the T99 with that log key I just talked about. 8 divided by 5.4, comma, and then put in the base, 1.0195. And you get and you get 20.3519. 20.3519 for the time. Or since 1990 and 20 is 2010. 2010 is when the population will be at 8 billion. Now here's the other approach, option 2, and some kids like this more because they don't like having to do this rearranging. Let's look back again at what we had here. 8 over 5.4, 8 over 5.4 equals 1.0195 to the t. They just like taking the natural log of both sides, or you could do the common log too, but you just take the natural log of both sides because the key is right there on your calculator above the x. 1.0195 raised to the t. And then they can use the bump the log rule to bring the t down. T times the natural log of 1.0195. And so we get t equals the natural log of 8 over 5.4 divided by the natural log of 1.0195. And you get the same answer. T equals, let's just check it on the calculator, And sure enough, again, you get 20.3519. And in other words, in 2010, the population hits 8 billion. Hold the bus. World population just hit 7 billion on Halloween this year, 2011. So let's come up with a more accurate rate of growth for the world population since 1990, when it was 5.4 billion. First of all, let's just check this on Wikipedia. And here's the population status. So in 1990, yeah, I guess I can go with this. They said 5.4 billion is more like 5.3 billion, both by the U.S. Census Bureau and also by United Nations Department of Economic and Social Affairs. Okay. So, and like here, they did a good job predicting whenever this came out. Somewhere between 2010 and 2015, we hit 7 billion. So it happened in 2011. So let's see what population growth has been. And to do that, we can use this again and say, if we hit 7 billion, and we start off at 5.4 billion, and that was from 1990 to 2011. 2011 minus 1990 is 21 years. So that's going to be 1 plus r to the 21st. Notice this is not a log problem. When the unknown is in the base, then it's just a matter of taking the 21st root. So 1 plus r equals 7 over 5.4 to the 1/21st power. So for 1 plus r, I get 1.012434. So r equals 0.012434. So the growth rate has been more like 1.24%, growing much less than they thought it would be happening at in 1990, which was 1.95, almost 2%. And here it's closer to 1.24%. So maybe population growth is slowing down. Okay, now let's do an investment problem. Suppose you invest P dollars at an annual rate of 6% compounded daily. How long does it take to increase your investment by 50%? Well, this is practically continuous if you're compounding daily. I think we found in some of our calculations that there wasn't even a difference in the nearest penny. And of course it depends on how much you're looking at, and if you're dealing with millions of invested dollars and so forth, you might want to look at it more exactly with the compound interest formula. But we're just going to use this formula and look at the idea of how long does it take to increase your investment by 50%. So the amount you have is going to be the principal plus 50% of the principal. That's what we mean by a 50% increase. So the amount equals P plus 0.5P, or the amount is 1.5P. So replace the amount with 1.5P equals P times e to the interest rate, put it as a decimal, 0.06T. And so now, when you thought maybe you had too many unknowns, you actually only have one. And that is basically your unknown time. So 0.06T will equal the natural log of 1.5. So you get T equals the natural log of 1.5 over 0.06. And that works out to be 6.76 years to get to 50% more of your money. Now let's contrast that, same kind of problem, but now how long does it take to double your money? So now the amount will equal twice the principal. So 2p equals p times e to the rt. Cancel out the p's. And so we get rt equals the natural log of 2. So t equals the natural log of 2 divided by the interest rate. And the natural log of 2 is about 0.693 divided by the interest rate. In this case, the interest rate was 0.06. Got to put it in as a decimal. Let's see what that works out to be. And you get 11.55 years. So roughly 11 and a half years. Now contrast that with the rule of 72. The time it takes to double your money, the time to double is roughly 72 divided by the interest rate as a percent. 72 divided by 6 in this case is 12 years. So the rule of 72 did come up with a nice estimate. Actually, it should be the rule of 69.3, but I think 72 is a much nicer number for other things to go into, so that's why they generally call it a rule of thumb. Okay, now homework examples. Let's take a look at this one. Solving 3 to 2x minus 5 times 3 to x plus 5, 4 equals 0. This is actually in quadratic form because one expression is the perfect square of the other. 3 to the 2x equals 3 to the x squared. So we could let u equal 3 to the x. And so u squared equals 3 to the 2x. So you can transform this equation into u squared minus 5u plus 4 equals 0. And that's easily factored, u minus 4 times u minus 1. So you get u equals 4 or u equals 1. But be careful with using substitution techniques. You do have to sort of unsubstitute at the end here. So with u equals 4, we have 3 to the x equals 4. So you get x equals the log base 3 of 4. With u equaling 1, we have 3 to the x equals 1, or x equals the log base 3 of 1. Well, any base b of 1 is 0. So we get x equals 0, or x equals log base 3 of 4. And that's why I said you could leave it like that here. You can express the answer as a log. Because it didn't say calculate, it just said give the exact answer. So assume I want the exact answer if I don't say calculate. 2 answers on that one. Let's check them real quick. You put in 0. 3 to the 0 is 1. 1. So 1 and 4 is 5. 5 minus 5 is 0. That checks out. Log base 3 of 4 is a little trickier, but when you put the log base 3 of 4 in here, you just get 4, so you get minus 20 there. Log base 3 of 4 here is going to be log base 3 of 16. So 16 and 4 is 20 minus 20 equals 0. So they both check out. Now evaluate each expression. You can use the results of 35. That is the log base b of c equals 1 over log base b of c. And you can, oh dear, I forgot to change this. This should be log base, excuse me. Equals 1 over the log base c of b. Got that fixed. Okay. So when we do this, we can try and get these both into log base 8s, because watch what happens here. This is 1 over the log base 8 of 25 times the log base 8 of 5. And so it's the log base 8 of 5 over the log base 8 of 25. Now you got a couple things you can do here. You can actually see that this is equal to the log base 25 of 5. And what power do you raise 25 to get 5? You raise it to the 1/2 power. Or you can say, okay, you got the log base 8 of 5 over the log base 8 of 25. We could change log base 8 of 25 and log base 8 of 5 squared, then use the bump the log rule. So log base 8 of 5 over twice the log base 8 of 5. And log base 8s of 5 cancel out, and you get 1/2 that way too. That's it. Flange out.